Newton's second law of motion is F equals to ma, where the capital F is force, and this force is not just any force, it is the sum of all of the forces, or the net force. So this equals to ma. The m is for mass, and you already know this a is for acceleration. So this equation basically tells you that for the same mass, if you wish to provide twice the acceleration, you will need twice the net force. And for the same acceleration, if you double the mass, you will need to double the net force as well. Also, acceleration is a vector. What about mass and the force? Mass is a scalar, but the force is a vector. Because mass can only be positive, that means the acceleration and the net force must carry the same sign, and therefore acceleration and net force must always be in the same direction. Here's a puzzle for you. I have a spool with thread going around, and the string comes out. Now I'm going to put the spool on a table. And for this one, the string goes around and comes out from the top. I pull on the string to the right. Which way would the spool go? Would the spool go to the right, to the left, or stay in place? What if I flip it over so it's like this? The string goes around and then come out underneath. When I pull on the string to the right, is this spool going to move to the right, to the left, or stay in place? Now this is my spool, and I have the string wrapped around, and now the string comes out from the top. And I put it on the table, and I'm going to pull to the right. And the spool goes to the right. And then I'm going to flip it over. This time the string comes out from underneath. And I put it on the table and pull to the right again. Again, the spool goes to the right. If you remember, for the Newton's second law, net force equals to ma. The acceleration and net force, they are always in the same direction. So if I pull with a rightward force, there's no reason why the spool should go to the left. Now let's look at this example. If you wish to provide a 2 kilogram object a 3 meters per second squared acceleration, how much net force is needed? Since the net force equals to ma and the mass is 2 kilograms, the acceleration is 3, so I'm going to get 6. Since we're multiplying the kilograms by the meters per second squared, I'm going to get 6 kilograms times meters per second squared. This is the standard unit for force. And we give it a special name, we call it newtons. So this will be 6N for newtons. So to be consistent, if we use newtons or kilograms meters per second squared in our equation, we must use standard units for everything else we plug into that same equation. Now let's look at weight and mass. In our daily life, we usually treat weight and mass as the same thing. But in physics, they are different. Weight is the gravitational force acting on an object, while mass is how much stuff you have in an object. I know that when this ball is in free fall, gravity is the only force acting on it. So the gravitational force is the net force on the ball while it is falling. I also know that while it is falling, its acceleration is the gravitational acceleration g. Which means while falling, the net force is the gravitational force, is the weight of the object. And since the net force equals to ma, and while falling, the acceleration is the gravitational acceleration g. That means weight equals to mg. So, if you have a 1 kilogram object, the weight mg would be 1 times 9.8, would be 9.8 newtons. If everything I put in is in standard units, 1 kilogram, 9.8 meters per second squared, I'm going to get the force that's in newtons. Of course, I can round this to 10 newtons. Here I have a 1 kilogram and a scale that measures force in newtons. So if I hand this 1 kilogram here, you can see that it reads about 9.8 newtons. It's a little over 10, but that's just because it's not a very accurate scale. If I take this 1 kilogram to the moon, where the gravitational acceleration g is about 1/6 that on Earth, this block would weigh 10 divided by 6, 10/6 of a newton. But its mass would still be the same 1 kilogram. If I take this to outer space very, very far away from everything, when I let it go, it would not fall, which means g is 0. It would weigh nothing, but its mass would still be the same 1 kilogram. Before we end this video lesson, I would like to talk a little more about forces. You all know that a force is basically a push or a pull. So to measure a force, we can use these spring scales. This one measures how hard I pull. And this bathroom scale measures how hard I push. When we exert a force on an object, something always happens. What do you think always comes with a force? It's not acceleration. Of course, sometimes the force can produce acceleration, but not always. For example, I'm pushing on this book, but not hard enough, so there is no acceleration. Or I can push on this table. There's a force acting on the table, but there's no acceleration produced. What always happens is deformation. Deformation. That's why we can use the amount of deformation of the springs inside this spring scale and the bathroom scale to measure forces. It's obvious that when you exert a force on certain things, you get deformation. But when I push on the wall or on this table, it's kind of difficult to see any deformation because the wall and the table are too hard to have obvious deformation. But the deformation is there, and I have something I can use to show you. First, I want to show you that the steel white column on the left side of the screen is in my basement supporting my house. Just want to show you that this is a steel column. This is a magnet. Okay. And I have a meter stick duct taped to the column, which means if I exert a force and cause a deformation on the column, the meter stick will get brought in as I get a dent on the column. Of course, the meter stick is only going to move a little bit and we won't be able to really see it, but I can magnify that effect with this pin. I got a pin with a little piece of mirror taped onto it. And I put this mirror underneath the meter stick. Which means when the meter stick moves in that way a little bit, the pin is going to rotate very slightly. Now you still won't be able to see that, but if I can shine a laser beam at the mirror, that reflection from the laser beam. If I shine a laser beam at the mirror and we look at the reflection, As the mirror rotates, we'll be able to see the reflection move. So here, the laser beam goes down, hits the mirror, and gets reflected. See, here's the reflection, and the reflection goes that way and hits the wall. Okay, so if I exert a force on the column, the deformation will bring the meter stick in, rotating the pin, and therefore rotates the mirror. You see, the reflection moves because of the rotation of the mirror. Even though the mirror rotates very slightly for very small angle over long distance, the length of the arc will be large enough for us to see, and that's what you see, the motion of the laser beam on the wall right there. So this allows you to see the effect of deformation caused by my force. Right there. Another interesting example of force causing deformation is tide. The body of water on the surface of the Earth experiences gravitational force from the moon and the sun. Over here, I'm only looking at the force from the moon. So the water gets pulled and elongates along the direction of the pull. So you get the normal kind of tide about twice a day because of the Earth's spin. By the way, this is not drawn to scale. I exaggerated the deformation of water. In reality, tide is more complicated because there are many factors affecting tide. Those factors include the orbiting of the moon around the Earth, the sun's gravitational force, the Earth's spin, the shape of shoreline, the depth of water, etc. To see some nice animation on tide, I have included a couple of links in the description of this video and at my website. I will see you next time for Newton's third law of motion.